The rate of a chemical reaction is a measure of how fast the reaction proceeds. Equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. So the rate, again, is how fast it proceeds, and the rate of the reaction is going to depend on several things. One way to measure that rate is to look at the amount of reactant that changes to product within a given period of time. We are not going to be measuring reaction rates. That's for a more advanced class, but we just need to have an idea of what it means. When we understand what controls the reaction rates, I can't talk today either. When we understand the factors that influence reaction rates, then we can exert some control over them and make them do more what we want them to do. So collision theory is one theory that it helps us to understand how reactions occur and what's going on with that. So in collision theory, we think about chemical reactions occurring through collisions between molecules or atoms. So this is the example we're going to look at for a while. Hydrogen molecule reacting with an iodine molecule to form two molecules of hydrogen iodide. So in order for those molecules to react with each other, they have to bump into each other. They need to bump into each other with enough energy for the reaction to proceed and form the products. That collision energy is related to the particle velocity. So how fast they're moving is going to affect how much energy they have.
Is that like why heat can help reactions because it speeds up the particles?
Yes, that is why heat can make reactions go faster. Because when you heat a reaction, the particles are moving faster. Not only are they running into each other harder, so they've got more energy, but they're also going to collide more frequently. Okay? So my weird analogy for this is you think about meeting someone and getting involved in a relationship. So in order to get involved in a relationship with someone, you have to meet them, right? If you don't know they exist, you can't have a relationship, right? So in order for these two molecules to interact, they have to bump into each other. They don't have cell phones and internet dating services. They actually have to physically meet. They also need to meet under the right circumstances. We've all heard stories of people who, bumped into each other literally, and then got into a relationship years later because the first meeting was just not favorable for them to like each other. So collision energy is related to particle velocity. When we talk about the average energy, especially in the gas phase, some of them have high energy, some have low energy. So even though it may be at a cold temperature and overall low thermal energy, there may be some of those molecules that do have a higher energy. And if those bump into each other, they can react. The high energy collisions are going to lead to products. The low energy collisions are not. Most chemical reactions have what we call an activation energy. This is an energy barrier that must be overcome in order for the reaction to proceed. So it's a little like a bump in the road, a fence. It's something you have to get over. It's an obstacle. If you have enough energy to get over the obstacle, then it's clear sailing. But if you don't have enough energy to get over that obstacle, you're not going to make it through. One thing that the activation energy may be caused by is the energy needed to break existing bonds. So in this example with the hydrogen and the iodine, each of these is a molecule and there is a bond holding the two atoms together. In order for the reaction to occur, you have to break those bonds, and that requires some energy. The factors that influence the rate of the reaction are going to be the same factors that affect how many high energy collisions there are per given unit of time. So let's look at some pictures here. Let's see what concentration does. Here we have a low concentration of our reacting molecules. When there's very few molecules in this volume, then they're not going to run into each other as frequently as when you have a high concentration, right? This is why people go to places like bars and parties to meet people, because there's lots of people in a small space. You do not go to Wyoming if you want to meet people, because it's mostly empty. I have nothing against Wyoming, but it's got a very low population density. So a low concentration means you're going to have very few collisions relative to a higher concentration. And so the initial rate of reaction will be slow for low concentration. Now we also need to think about, well, what happens as this reaction proceeds? Even at this high initial concentration, as the reaction proceeds, as we think about these molecules running into each other and getting involved in relationships, what happens to the number of available molecules? It goes down, right? You know, this molecule and that molecule get together and make new molecules. And these two get together, and those two get together. As the reaction proceeds, the concentrations of the reactants decrease, and the rate of the reaction decreases. Make sure I'm not skipping something because they kind of look alike. So concentration affects the rate. Temperature affects the rate. Most reactions will go faster at higher temperatures because as you increase the temperature, the molecules are going to move faster. You're going to have more collisions, and you're going to have higher energy collisions. So here at low temperature, the molecules are moving slowly. They're going to bump into each other, but not as frequently as at a high temperature. And some of those collisions aren't going to have enough energy to make anything happen. So high temperature, faster rate. Any questions so far? This would be like speed dating. You go to the bar and they've got all these tables set up, and you got like 5 minutes to talk to this person. They hit the bell, and then everybody scrambles around. Not that I have ever done that, but I have seen it on TV shows because that came about after I was already married. Thank goodness. When they're moving about quickly, they're going to interact with more molecules. There'll be more collisions, and so the likelihood of having a reaction occur is greater than if people are just sitting around in the bar. Maybe there's the same number of people, but they're all just sitting there staring at their beers, right? Not much relationship making is going to happen. So the summary is, reaction rates will increase with increasing concentration of reactants, and they will increase with increasing temperature, and the reaction rate decreases as the reaction proceeds. These are generalizations. There are exceptions, of course. So, conceptual checkpoint. In a chemical reaction between two gases, you would expect that increasing the pressure of the gases would probably increase the rate, decrease the rate, or not affect the rate. Increase. When you increase the pressure of a gas, how can you do that? You can compress it. You squeeze it into a smaller volume. What does that do to the concentration of the gas molecules? It increases it. You have more particles in a smaller amount of area. And so that's the equivalent of increasing the temperature, increasing the concentration. So that would increase the reaction rate. Okay?